Welcome to Natural Habitat Adventures Daily Dose of Nature. I'm your host, Kendall Bauer. Today's presentation is From Mind Maps to Migration, Navigation in the Animal Kingdom, presented by NetHab Expedition Leader Kristina Disney. Kristina, I'm so happy to have you here. I'm going to hand it off to you.
Thank you so much, Kendall, and happy we got to have a quick hi today. I'm very excited to have you around. And hello, everyone who's joining in today. Thank you so much for joining. This is a fun, fabulous topic, in my opinion. Navigation is something that I have always nerded out about, and I think is just kind of this fascinating thing of how we solve it in all these different ways. And I can even remember for myself, I swear I can remember, I don't know how old I was, but I can remember sitting in my kitchen and remember the exact moment where I was like, hey, north is this way. And then it was just true, right? It was this thing that was suddenly just true for my whole life. And I could start figuring out and building um, how to like navigate the world from that other way, right? And so there's all these different ways that we do it because we are also animals, right? We also count in that animal kingdom. And so to give us some realm of appreciation, I'm going to start us off with some human navigation, right? So really, when you think about human populations, they've been historically nomadic over sedentary for most of the time. Obviously, we get the development of agriculture, changing, shifting cultures, but even today, right, there are still lots of nomadic cultures. And so that ability to move, to find the same place, to return, right, it goes off of lots of different features. We're talking about landscape features, some that we either, track or create ourselves, or just using what's already there. And I would argue, though, that certainly our navigation across land has been very spectacular. But I think where it really shines is humans voyaging across the sea, right? In olden times, if we go back to the ancient days, with sailors, they always stayed close to shore because they didn't have the ability to find their way across the open ocean. But that, of course, changed as humans kept growing and thinking and trying to solve this problem of wanting to get somewhere they hadn't been yet, right? I'm sure my travelers out there can identify with that. So it wasn't really until we have the Vikings and the Minoans. So we're thinking about the Minoans, that's the Mediterranean. And we have evidence that they were using stars to navigate between 3000 and 1000 BC, right? There's evidence left behind of it. So humans have figured out how to use patterns and recognize that for a long time. And the better we've gotten at it, the more exploring we've done. You and I might take for granted the notion of a compass, but that was really only invented around somewhere between 200 BC and 180, right? So roughly about 2000 odd years ago, someone figured out that we have magnetism on our Earth, and that we could start using it to thinking about what direction we wanted to go. Now, our first compasses were not quite so compact or hidden away as they are today. The first ones were invented by the Han Dynasty, so again, around 2000 years ago, and the name would translate into south pointing fish, right? So back then, they had the lodestones, right? So it's some form of iron that can take on magnetism, and the south pointing fish, so they would make it so that the mouth of the fish would be directed to go south. So old school compasses, they were working on either the surface tension and having it float on water, or again, the string. And the Chinese were not the only culture to have those. Lots of different other folks did, either simultaneous or later on, but we'll just say these are kind of the first recorded evidence of them. And so when we have that, that starts to sort of increase our accuracy of movement, let's say, or making more conscious choices. Before we're following trends and patterns and seasonality, but the more details that we have, the more precisely that we can navigate. And one thing I think folks often don't think about is the importance of time when it comes to navigation. So it's a very Canadian thing, but something, and maybe other folks do it too, but I know that some of my international friends always call me on this and laugh about it. But when I talk about how far away something is, or if I'm going to travel somewhere, I will say it's a 2-hour drive away. I don't say how far it is, or right, I'm using the time to communicate the notion of travel, which is sort of a silly thing in some ways, because if it's 2 hours away, if you're in the city, that could be across town during rush hour, Or if you're out in the country like where I grew up, that means you're driving 200 kilometers. But you're associating sort of that mental voyage, that distance and time relationship is really, really important. And it's not just sort of culturally, it's important to how precise we can measure distances in and of itself, right? So as we started dividing our day into 24 hours and 60-minute chunks, right? If you've ever stopped to think about it, we have minutes and then we have seconds. If you stop and think about why is a second called a second, well, it was the second division after minutes. And so once we could start counting seconds, once we got clocks that could do these very teeny tiny segments of time, then we could start having really good precision in our movements. And so that spurred this whole explosion of discovery and of navigation. So what you're looking at on the left side is a cross staff, which was invented in the 1300s. If you want to pull really deeply out of the recesses of your minds, Pythagoras' theorem from school, right? You've got a triangle, you can figure out the distance and the angle, right? Looking at the sun and the stars. It gets more and more complex as time goes by. We invent the quadrat in the 1600s. Again, different angles, especially really important for navigation. The one on the right is a sextant. So a lot of our sailors, again, a lot of this comes back to navigation on the water, because in the water we don't have landmarks. We have to rely on this broader sense or this other way of navigation because we can't use cues, right? All the ocean, and this is an over-exaggeration for my mariners out there, but it looks very similar, right? So how are you going to find your way out there? My personal favorite is the astrolabe, which is essentially like a time multi-tool, or it's like the calculator of this what is that, 15th century, 1400s. So it had all these 3 different dials, and one of them you adjusted for the zodiac constellations, and then you also adjusted to get yourself set up to determine your elevation. You could figure out your latitude from it. And you could even tell time with it. And it was all come back by turning these 3 different circulating discs in it. So I would actually, well, I've always wanted these. Eventually I will time travel, but I also need to learn how to use one. So maybe I don't have to time travel. Maybe I could just get one in modern day. So speaking of modern day, we don't use astrolabes and sextants anymore, right? Around our atmosphere, we have, I wanted to say hundreds, but I'm probably terrified, and to more correctly say thousands of satellites that are currently circulating our globe, and they are communicating with us on the regular, even if we don't even realize it, right? I am just as guilty as the next person. My smartphone is very rarely more than an arm's length from my body, because we're so used to having it, to navigating, right? And I wonder now, everyone, it's a very generational thing, but if I had grown up with a smartphone, would I still have figured out where north was at the age of 8 or 9? I don't know, right? Because right now, my navigation skills might even gone down from my childhood because I'm relying on that to do much of the thinking for me. So hopefully you're still with me. Hopefully you're not lost yet. You might be wondering, where are my fuzzy, furry, feathered friends? I thought we were here to talk about animal navigation. Well, I wanted to start here because, one, I think it's always important that humans are animals too, right? I think that segregation between us and them is what creates a lot of problems. So I'm always happy to push that narrative. But the second reason is that I wanted to sort of show this trajectory of how much more clever we've gotten at navigating, because the same is true in the animal kingdom. They have been evolving to be masters of navigation alongside us, and they can do it in all of these very fantastic different ways. So I want to sort of start us off with a story. So this is where I grew up in southern Saskatchewan, and it's one of sort of the corner of Saskatchewan that I grew up in is one of the largest tracts of native prairie that's still retained. And one of the things that we have there, we have one of Canada's younger national parks called Grasslands National Park. What we got is a lot of grass, so the grass is what we've preserved. And what is sort of fascinating, and I've been fascinated again since my childhood, is that this is one of the places that the bison were reintroduced. So yeah, for most folks maybe who do or don't know, the plains bison was nearly almost completely decimated I think the numbers were down to less than 100 out of what was projected to be somewhere between, depending on who you talk to with the numbers, anywhere from 10 million to 30 million across the prairies. And that's into the States and Canada as well. That's a contiguous area. And so they were completely decimated. There's pretty much like one farm or a couple farms that had a few of them left. Again, somewhat domesticated, but they were introduced into Elk Island National Park, which is in Alberta. And once that population, right, think about these are large migrating species. They need a lot of space. And so now when we again think about being less nomadic as a culture, think about farmland, it's always boxed in. They don't want a herd of bison passing through. So Elk Island National Park eventually reached carrying capacity. And so they had to come up with different solutions for that. Some of it was indigenous harvesting. Some of it was seeing if other parks were interested. And so I said that our park, Grasslands National Park, was a younger park. And they started looking into whether or not they could take on bison. And so they decided eventually, as per usual, all of the bureaucratic hoops were jumped through. And they brought the bison to the park. I can't even remember how many pairs they started with in the beginning. But I went there as a kid on a school tour about 10 years after the bison had been transplanted here. And this is one thing that still kind of boggles my mind. But 10 years on after those bison were there, they only ever hung out in the northwest corner of the park. It was a huge, huge national park, massive. And even though they had all this space to roam, they wouldn't leave this one corner. Now, the northwest corner of the park is the closest they could get to getting back to where they came from. These bison had been trucked, right? They didn't walk or run there. They had been hauled from Elk Island National Park, which is sort of, we'll say central Alberta, for those who are checking out the map, down to southern Saskatchewan. So we're, straight line distance of probably 650K, something like that. And it took them multiple generations before they stopped trying to escape the park to get back. And so this is kind of stuck with me for a very long time, right? They knew where they had come from and they had been trying to get back this whole time. And so this question of how could they possibly know where they came from, right? What in their mind, in their body, is telling them where home is or was? So we're going to talk about a few different methods of navigation today. There are many more than this. And we are going to answer the bison story. I promise to bring us back around. So don't worry, I'm just leaving it a cliffhanger for now. So we're going to talk about how animals use celestial objects, how they build mental maps, how they rely on smells, pheromones, and magnetic fields. So let's start with the sun first, right? And really, we do this too. We just kind of have disconnected with a little bit. But essentially, you can always tell where you're going if you can keep track of where the sun is in the sky. Now, that would be pretty easy if our sun stayed in the same spot, right? But it doesn't because our wonderful Earth keeps rotating and spinning us around. And it also changes on its own angle. So there's all these things, right? We have seasonality, the sun changes the altitude in the sky, and it also changes what time of the day it rises. So it's pretty hard to always figure out where you're going if the thing you're using to navigating is also moving. Well, the way animals have solved this is they do something that we call time-compensated sun navigation. Or sun compass. So the sun's always moving, and so what animals are doing is they sync up their circadian rhythm with the azimuth, so that's the angle of the sun, and they time that with their internal clock. So those are kind of a lot of things all together. So let's break that apart one by one by one. So one thing that humans have retained, we might have lost some of our cool ability to smell and, potentially some hearing things, but one thing we have retained is that we still have our circadian rhythm, just like other animals in the animal kingdom. And what that is, it's our body's response to daylight and to nighttime. It regulates our sleep, it regulates a lot of our health, our hormones. Also, everyone's circadian rhythm is a little bit different, right? Some people joke that they're nocturnal. Some people kind of really are, right? Their bodies want to stay up with that. But even though if you want to stay up at that time, your body is still clocking and it's still reacting to that change in daylight, right? For people who get sort of those seasonal blues, it's some of that sun coming back that cues different things in our bodies to come to life. And so that circadian rhythm, what's happening is they're timing it with the azimuth of the sun. So we know when the sun comes up, and then also there's the highest point. There's, let me think about this way. So we would talk about, if you ask anyone in the world, they would usually say, whatever language they might answer in, that the sun rises in the east and it sets in the west. We all agree on that. But we're also all over generalizing, because depending on where you are in the world, if you're in the northern hemisphere, right, it's actually rising in the southeast and then it's setting in the southwest. Or, right, if you flip hemispheres, or if you flip latitudes, flip seasons, right, that's actually, it's always the kind of this thing that's rocking back and forth across our sky. But we all just agree east and west as a general thing. But the trick is that if you can find the highest point, so wherever you are in the world today, the sun today at some point will be at its highest point before it starts going back down. Now, what many animals' bodies intuitively track is at the sun's highest point, what angle was it at? Was it at southeast? Was it at southeast east, right? That degree helps them know what direction they need to move from. So one, I think the fact that even just, subconsciously tracking that to a point that it's useful is amazing. But then some animals are even capable of communicating that navigation directly to others. So the first animal we're going to show who has a really cool example of time-compensated sun compasses is, in fact, the honeybee. And so these insects are incredible for so many reasons. But today, my favorite reason is because they do something called the waggle dance. Yes, it has a fantastic name, and I'm so happy that whatever scientist or person named it that stuck to their guns. What is the waggle dance? Well, bees are capable of tracking the location of the sun relative to their hive. So when they go out and they find food and they want everyone else to come back and, bring that pollen back from those flowers as well, right? Because they're working as a social, high functioning structure or society, you could say. They need that information to get out. And so they're not telling them all one by one. What they do is they actually go on the edge of the honeycomb vertically or on the bottom if in the circle. And what they do is that they will dance and vibrate. We're calling it dancing. Maybe they would call it something else. Relative to the angle of the direction of the food source from where the sun is. So if they're straight on, then it's straight the direction of the sun, and then the dance will shift depending on how far it is from degrees from the direction of the sun. Now, admittedly, that doesn't include distance, but the idea is just to get the whole sort of hive going in the general direction and then start ferrying food back. So it's a really, really cool example. Some scientists, this was like a really amazing sort of discovery of navigation and communication of navigation. There is a bit of sort of return, I'm going to say flack on this, which is that, so bees are really good at doing the waggle dance. They're very good at keeping that direction. But one thing that after scientists discovered this is that often they'll be dancing and none of the other bees will pay attention to them. So there'll be 6 bees dancing, or they'll only pay attention to one, or they won't notice the other. So it's kind of a bit funny that they go through all this effort to track what the direction that they're going, and then no one listens to them anyways. So anyways, bit of a humor line. I feel like there's some parallels probably into the human world, but I won't go there. I'll save it for the bees. But one of the ways, right, so just to say that, one of the ways they've kind of tested this and shown this is that they've taken hives in one location, and then they've picked them up and moved them to another one. And then on overcast days, when the sun isn't there, bees still navigate to the original hive location. So they kind of use a tree line or some sort of landmarker relative to that. There's the sun, there's their degrees. And so it's an active thing that's kind of imprinted, and then it stays with them. We jump to our next species, right? Species that fly, they're traveling lots of distances. So obviously these are ones we would be thinking about as far as quite impressive navigators in the world. So this is a starling, and there was a lot of research done on them, especially in the 1950s. Arguably I'd say one of the starlings, claim to fame was because they got brought here from Europe because someone really liked them in Shakespeare. And I'm not really sure if that's an urban legend or a true one. If anyone knows, feel free to leave it in the comments. But I always think about that and kind of laugh that Shakespeare is the reason why we have so many starlings. But anyways, so starlings are also pretty good movers and shakers. And so in the 1950s, they did a study where they wanted to shift the bird's perspective of the sun and see if navigation would shift with it as well. So what they did was they had them caged, and then they used mirrors to reflect and change the location of the sun. And when birds were then trying to migrate or trying to travel with intention, right, then they actually shifted whatever. So if they shifted the sun 90 degrees to the east, then the birds shifted their whole navigation pattern 90 degrees to the east, which is pretty amazing when you think about it. One, that someone thought through to figure out how could they move the sun for all of these birds, and obviously the actual navigation of the birds themselves. But if it hasn't already popped up into your mind, only half of our day is in sunshine. The other half of our day is nighttime, right? So what about nocturnal species? And when we think about songbirds, if I kind of stay in the world of birds, that's a really great example that most songbirds are are nocturnal migrants, right? So if you're not a late nighter or an early mourner or early waker, early riser, forgot about how that saying went there for a second, then you're unlikely to see lots of songbirds, right? That's why you can always hear them sort of in the morning. That's when they're most active, but they're also just in general, that's when they're passing through on their way to wherever it is they're either going to feeding or breeding grounds. So how are we going to figure out how birds at night are able to migrate? Well, we assume it had something to do with the stars. And so there was another scientist, and what he did was he hand raised a bunch of birds, and he did it in 4 corners of a room. And in each corner of the room, those chicks were raised under a different fake night sky. So they had a different pattern of stars, and they also had a different orientation. So some of them spun clockwise, some of them spun counterclockwise, right? Thinking about our world spinning around. And the birds that he'd used were garden warblers. And what they found was that the birds didn't keep track of the pattern of stars. So if they changed out the constellations that they had in their corner, it didn't matter. The bird could still migrate. But if they changed the rotation, then the bird would migrate a different way, which is what led us to realize that that lots of nighttime migrating birds are using the poles. So the notion that as the stars move, there's a fixed point, right? Really, that's us. It's not the stars moving, it's Earth moving, but we're thinking about perspectives here, right? So we have kind of 2 fixed points that everything else spins around. And so that's what makes our North Star famous, right? It's not that the North Star is actually the brightest. It's that if you're standing in the Northern Hemisphere, if you had the patience to sit up all night and not fall asleep, every other star would turn around the North Star in a complete cycle. Also, as a fun fact or something to keep track of as you're doing your own voyaging and your own traveling, wherever you're standing in the world at night, if you're at the equator to the North Pole, your latitude is the degree or the angle from the horizon up to where the North Star is, right? So if you're at the equator, that means that you look straight out, and that's where you find the North Star. If you are hanging out at 49 degrees, which is about where I am, that means that I have to look 49 degrees in the sky, and then I'll see the North Star. And if you're lucky enough to be hanging out at the North Pole, you just have to look straight up, and that's where you're going to find it. So next time you're trying to look for the North Pole or look for the North Star, there's a bit of a tip or a trick to find it. But so we go back to the garden warblers. So they're using that pole orientation. Now that's also true for the Southern Hemisphere, right? We're not leaving them out. Again, they don't have the exactness of the North Star there, but right, they've got, what's the closest constellation? Aurora Australis, I think it should be. So that's, or no, not Aurora Australis, Coronis Australis. It's the Southern Crown. So that's kind of the closest constellation that they can use for navigation in the Southern Hemisphere. So you still have to think it's kind of amazing, though, that for a lot of these these small birds and these songbirds, that solo migration that they managed to do it's pretty spectacular. Yes, they do have the ability to follow the stars, but there are also a whole boatload of other genetic, essentially kind of switches in their DNA that allow them to migrate that we're only just starting to understand now. And so the story will still continue, but I'm going to shift to maybe some other species and some other ways to navigate, and go check out some ones on the ground. We'll leave our feathered friends on the side for a moment. So I don't know how good everyone's memory is, but for some of us more than others, right, we are really, really good at remembering the exact location. I don't know if anyone right now can tell me where the exact location of your car keys are. Hopefully most people can know. Other people you know because of habit, right? You don't actually know where your car keys are, but you know the circuit route that you would have taken when you came home, set them down, and started putting your groceries in the fridge. Or you came home, you went upstairs, and you turned on the TV, right? You have this route in your mind that you've consciously or unconsciously sort of mentally mapped. So you're not necessarily looking for the thing, but you're looking for the route, and that's how you find yourself back to it, right? So when we think about mental maps, it's based off of exploration and clues. So an animal will orientate itself based off of features in its landscape. So if you change where the features are, it will actually make a miscalculation. But one of the ways that we know that this is sort of a cool application, especially studies in mice. So mice are not exploring out of necessity. Mice will keep exploring always. So the world starts off this big, and then they keep adding more and more information to it. So the further they explore, the larger the world becomes. And it's all mapped based from one cue to the next. Now, a really, really cool example and some very amazing, probably some of the world's most amazing mental mappers are the Saharan desert ants, or Cataglyphis fortis. And so these ants are doing that if we get fancy, we would call it path integration, right? So what that diagram on the right is showing you, so that's a 5 by 5 square meter, each one of those little dots. So it's actually quite a bit of distance. And so on the way out, so that's kind of the squiggly line, the ant is looking, it's exploring for food, it's trying to find it. Now, what's the most amazing thing is that it's essentially calculating every single one of its steps. It is doing mental math from the nest, every step it takes, plus minus, plus minus, plus minus, with every step, so that when it does find food, which is what that fun little black dot is, it's not going by sight, it's not going by, well, we'll get to smell, right? But in the case, it's not trails like other ants that you're thinking about. It is doing a beeline back because it has calculated the exact distance it is away from its nest. And so if we were to try and do this with a computer, it would take us, minutes, if not hours, to do the same thing that they are doing literally simultaneous to their steps, which is an amazing, amazing feat. So very, very impressive. Now, I kind of accidentally gave it away a little bit, but I said smell. Now, we don't often think about smells in the water, right? But there are smells in the water the same way that they are on land. Human sense of smell is certainly not the mightiest in the animal kingdom, because there is a whole world, there's a whole series of conversations that are happening around us that we are completely nose blind to, which was one of the things that makes me quite sad, actually. If I had a choice over any heightened sense, I think I would actually pick heightened smell. Again, you'd have more of the bad smells, but also just all of the cool things that are out there. And so it has to do with sort of this beaconing, right? And so there's, when we're looking at green turtles, these ones are studied off of Ascension Island, which is in the South Atlantic. So they're doing their larger scale migration, which we're going to get to how they're doing that. But once they're getting close to where they wanted to be, we're finding they're actually picking up currents of smell coming off of those islands, and that's what redirects their sort of general migration to these more localized places. And so even though those teeny tiny nostrils, you wonder what they're smelling all sorts of things in the water. And so there are sort of smells of our environment, but then there are also smells of the individual. And that really gets down to our pheromones. So it's another one, we kind of talk, as humans, we're certainly less conscious of it, I would say, than other species, or we've lost some of that conscious knowledge of it. But really, those pheromones communicate a huge amount of information. It's everything from who we are to what we're doing to what age cycle we're in. But in terms of navigation, it's essentially like the Hansel and Gretel breadcrumb, right? And so again, we jump back and think about our ants. So in addition to ones like the Saharan desert ant, which is using path integration, most ants have the ability to use pheromone trails. So what that is, right? So they're designed intentionally to be leading to a food source. And so what most people don't realize is that that pheromone trail for ants, it only lasts about 2 minutes. So that means it's a pretty functional thing, right? If you're going to a food source and coming back, if it's a good food source, then you'll use the same trail often and you'll keep it going. Or you think about more ants, food, lots of ants using the same trail, all of them will leave a higher concentration of pheromones, which means that the trail will last longer for people to find it. That sort of a funny thing that ties into that. If anyone in their childhood or more recently, no judgment, has eaten an ant, that really sort of sour smell or that funny acidic taste, that is actually the pheromone that your tongue is picking up. That's what you're experiencing there. So is their tracking pheromone, which I think is just kind of way too cool. But those pheromones exist in lots of different animals. I think ants are just the ones for us to sort of mentally understand the most, because pretty much any little kid anywhere in the world has hopefully gotten to lean over on the edge and watch them go from their nest and bring food back in. So again, just some other cool ones when we're thinking about pheromones and smells. And again, sort of jumping back into the aquatic realm, because I think it's one we tend to forget about a little bit, is that migrating salmon actually rely on smells quite a bit. There's a really cool study that was looking at olfactory cues and how salmon employ them. So most of the time they have, again, they're relying on their, let's see, let me back this up. They've got about a 7-year lifespan, depending on which species that we're talking about. So they are born in freshwater and they go spend most of their, say, teenage and adult lives in the ocean, and then they come back to spawn. And the majority of them come back to the exact same river that they were born in. However, and this is what I think is cool, because this is something that most people don't talk about, there are something that we call strays. So it doesn't mean that every salmon makes it back to the river they were born in. You could say some of them get lost, some of them get confused. Who knows what happens? Another thing that we don't often think about is that rivers can also change, right? They might not become habitable. Salmon might have to find a different one. So what we found in those is that in strays, their ability to smell gets super duper heightened, and they start looking for the smell of their own species to find a new river, which is so cool, right? They up that sense in their body in order to compensate for losing their source. So that's one of the ways that you can think about salmon expanding also, right? If you're doing well and they're in one stream, which I hope this is a story that comes true again, because a lot of our salmon are actually in decline, right? But the goal is that if we can up the number of salmon that we have in a healthy stream, then as that number starts to go on and it starts to get overcrowded, or we start to just statistically get more strays, then those salmon will hopefully start populating other rivers, or at least joining other species, other ones of their species, and growing beyond. And then even a next level that is super cool about that is that if a salmon is stressed, so I said that they're smelling their own species, they're looking for their own pheromone. Our pheromones, and our humans do too, we just are not nearly as aware of it, but they change depending on how we're feeling. So if a salmon is stressed, if it has been handled, if it has a parasite, then its pheromones change, and then if another salmon smells it, it doesn't want to follow those pheromones. It actually will avoid it, which I think is so cool. Again, thinking about, right, you've got an unhealthy river, you've got a stray salmon, that salmon is not going to choose that one, or at least not choose it after its first pick, which I think is so wild, so wild. All right, I think this is the last one. This is the one I've been dancing around a fair amount here, or at least one of the last main ones. I think it's one of the coolest ones, right? So if we go back to the discovery of the compass, right? That compass is using the magnetism of our whole world, right? So if we go just a little bit of geology for a second, think about the Earth. We've got a solid crust. Thankfully, very happy to all be standing on it. Then we have our magma, and then we have our core, right? And so that hard to believe, that fluid molten rock is turning, and we have our magnetic spheres traveling through it, right? So the angle of that is different depending on where you're at in the world. And also, one thing that we don't realize, so not only can we look at what magnetism we have in the present day, but we can actually track how magnetism has changed through Earth's time. And we're not the only ones that can do it. So can some animals, specifically a lot of our ocean goers. So sea turtles this is one of the coolest things I think about them, besides, again, them looking so darn cool, and such cute little faces. But so our sea floor, I'm going to do, again, hopefully it'll be a 3-minute geology lesson, but I promise it'll be worth it, right? So we are all standing on the surface of the Earth, on the crust. Our crust, we have some of the plates are above the ocean, some of them are below, but they're all connected in different ways. And some of our plates are growing apart. So they're new sort of molten rock, magma's coming to the surface, hardening and getting pulled aside. Some of them are getting smashed together. So those are converging plates where one runs over the top, goes down, that creates mountains, that creates volcanoes, things like that. But the one we're interested in terms of navigation, is we're interested in the diverging plates. So that's actually what the North Atlantic Ridge is, right? So if we look in the middle here, and that's where Iceland hangs out, but sort of what splits up. So the Pacific is the biggest ocean now, but if anyone wants to hang out for a few million odd years, the Atlantic is getting bigger and the Pacific is getting smaller. So the Atlantic, as it's coming out and it's cooling, so let's go back to our south pointing fish. Let's go back to our compass, right? The electrons in iron, when it's still, when it hasn't solidified yet, it has a preference for north and south, right? They get lined up in the same way that our Earth has that fun magnetic sphere going through it. And so as the rock cools, those electrons get trapped wherever they're hanging out at. So what that means is that if you look at the ocean floor, let's look at the Atlantic here for a second. So red is the newest, then yellow, then green, then blue is the oldest kind of thing. Well, we don't think about it because, again, it happens on a scale of time that is beyond us. But our Earth's magnetic field does change, right? For anyone who is a cartographer, we have to do declination corrections every so many years because the North Pole kind of wobbles a bit. And when it wobbles, and whatever new molten rock is coming to the surface, it gets frozen in time. It gets frozen in that rock with the direction of the orientation. So while you and I might look at the bottom of the seafloor and just see a bunch of rocks, if you are a sea turtle, which is so cool, they have the ability to sense how those different magnetic strips have sort of solidified in the Earth, and they can use them basically as mental highways of like, oh, here's this, here's the 300 years where we were like this, and then they're bigger than that, 3 million, let's say. But the point is that it's got these magnetic bands that they use for navigating. So as you can tell, I think it's super duper cool. But how did we figure this out? How in the world did we find out that they're using it for navigation? Well, thankfully, lots of other really cool things have been invented. And while they get used for, maybe improving electric cars or who knows, but thankfully some biologist was out there and was like, wait a second, I want to use it to mess with the magnetic field of animals to find out how they navigate. Sorry, I mean that in a kind way. I don't mean mess in a bad way. But Tesla coils. So Tesla coils, when you use them, they disrupt the magnetic field, and it does it in 2 different ways. So one is it can change the poles. So it can flip north from south. It can make it look like that in the field that you're in. The other thing, this is kind of maybe a hard one to visualize, but depending on where you're at in the world, and so think about our Earth is kind of like, it's got these 2 circles, and that magnetic sphere is going around. That's also why we get northern lights at the bottom and the top. It has to do with that flow of energy. So depending on where you're at in the world, you feel that flow on a different inclination. You think about it at a different angle from where you're standing. So Tesla coils can mess with what pole it is. They can also mess with that inclination angle. And so they can turn off the poles on some species and turn them back on others. And that's how we're able to figure out which animals are relying on pole orientation versus inclination. So when I was talking about sea turtles, they're relying on inclination to figure out those bands in the sea floor of what angle it was frozen, it was solidified at, and using that to migrate. Now, so far we've been talking about what they're interpreting from the outside world, but how is it, what in their own bodies, what in hopefully our bodies, wink, wink, can be used for navigation? What part of it? Well, for most species, for quite a few of them, they're actually specialized cells that either exist in the nose or in the eye. And so for trout, you find them in the nose, and they have about 1 in about 10,000 of their cells. They have cells that respond to magnetism, right? For lots of different bird species, it's in the eyes. Those are called cryochrome cells. And so, there is a sort of going theory that they can actually, quote unquote, see magnetism, whether or not you want to think about it that way. But it's a cool notion, right? But it's a notion that those cells are responding, right? They've got little bits of iron in them. That's the simplest way to think about it. And they're responding to very finely attuned changes in magnetism. So there are so many different ways, right, that animals can find their way home or to sort of complete migration routes. The trick is that different animals have different life cycles, different niches, and so that decides which method they're going to employ over others, right? So I think we called it from mind maps to migration, right? So if you're an animal that migrates, recovering thousands of kilometers, they're more likely relying on things like time compensated compasses and polarity, right? So they're looking at the magnetism. Whereas if you have animals that have home ranges, right? So what that means is that they're not necessarily completing this larger cycle. They have somewhere they go and come back. So that would be like birds hunting, even mice and nests, things like that. They're trying to get back to the same place. So those would be ones that are employing more things like mental maps, things like that. But the reality is that same as us, right? There's sort of this mix and match of different cues that they're relying more heavily on than others. And so one sort of last one we'll talk about here. How are we doing on time? Oh yeah, we're good. So it's this notion that of sort of taking in your environment and all of these different cues, consciously or subconsciously, in order to get yourself where you need to be. I think I kind of realized in myself, I don't know, probably in the last couple of years, I'm more of a mental mapper, or right. So I keep track of items, and then that's how I orientate from it. Sometimes in the city, I'll lose track of where north is, but I'll always keep track of. I can always get back to where I came from, kind of like the ant, right? But all of those cues can come together in lots of different ways. So a really cool one, which is what made pigeons so famous, right, is that ability to imprint. So from the moment a pigeon first takes flight, that first flight is so incredibly important. Not only is it to get over that big scary notion of jumping out of the nest, but when they go up and they take those first couple loops around, that gets imprinted as their home location, which is why they were used for messengers for so many years. It's because you could then take a pigeon, didn't have to fly there, anywhere in the world, and you could release it. And even years later, depending on how far away you took, it would still come back to that very, very first place that it imprinted. And that's using, again, a combination of magnetite, of marker cues, but really it's an internal compass that's bringing it home, which is pretty spectacular. So just with the time left, I kind of want to go through a few specific species that I think are such incredible navigators because of the journeys that they take. And the first one I'm going to start us off with here is one that I hope everyone can't help but love, but it's the monarch butterfly. These truly are some of the greatest navigators in the whole world, right? They've got a journey that can be around 4,000 kilometers that spans multiple generations, which just is kind of mind-blowing. It was like grandmother butterfly took you here, had you, and then you're still going to make your way back, right? It's they're one of the most certainly best studied species, right? And they're relying on what seems to be a sun compass as well as temperature cues. So temperature cues is one that we're, sort of worried about as our world continues to change, because that might dislodge a lot of cues, right? Those environmental cues that they're looking for those big migrations. But they're starting off, they're wintering. They're all trying to get to the mountains in Mexico in order to winter. And then what will happen is then as the, milkweed, so you get the right one, as that starts to come into bloom further north in the States, then multiple generations of monarch butterflies start to travel north with it. And then this is the cool thing about the generational bit, is that there are breeding generations, and then there are, we'll call them traveling generations. So there is actually a hormone, right? So again, thinking about pheromones, we're going back to that same category of things in our bodies. This one isn't about communicating with each other. It's a control inside of the monarch's own body. So there's a hormone that goes into place in the juvenile phase that stops it from going into reproduction, or I should say prolongs it. The reason being is that they put more energy and having that ability to make that long trek back come the wintertime. So there's breeding generations on the way up, and then we have a return generation coming back. And we go from really small to really, really big. Again, another one of the most amazing migrators, I would certainly argue, is the humpback whale. And a very cool thing about humpbacks, gray whales. I'm jumping around here. Right, so gray whales are doing one of the largest migrations. They're going all the way down from the coast of Baja all the way up to Alaska and all along that coast, right? So they also have small amounts of magnetite in their skull. So those little tiny cells are inside their cells that we think are capable of checking in on the Earth's magnetism. And so they are using, right, it's sort of crazy to think about an animal that is literally tons using cells that would fit, essentially in your pinky to make such a large migration all the way across the world, which is pretty darn wild. And second last one, right? Now, the last couple examples, so we've got sun compass with the monarch butterflies, we've got magnetite with the gray whales. Now, polar bears. This is one really fun thing to think about with Arctic species. Because they are so close to the magnetic pole, magnetite is actually really unhelpful for them because they're super close to the North Pole. So there's another thing, this is true of any navigation, but something to think about if you're traveling with a compass. The closer you get to the North Pole, the less accurate it is because you're so close to it, right? It's like you could move a little bit and then it jumps way over here. And also the magnetism also shifts even on a daily basis. So for a polar bear, that's not helpful. But they live on the sea ice and they are very, very good. They're quite the travelers, right? But you can think about they're essentially living on a conveyor belt, which means that the sea ice is always moving, but they are able to keep themselves in roughly the same place if there's a good feeding spot there, right? So they're able to track the wobbly magnetite, but when they're trying to track each other, what they're actually doing is they're looking at the pheromones between their paws. So lots of bears rely on that, but polar bears especially, right? So they have glands between their toes, which then emit a pheromone. And as we've been able to study more and more of, we're realizing that those pheromones don't just they can tell the age, the sex, and there are a bunch of compounds there that we haven't even identified yet. So we might even think that it kind of might be like dolphin calls or signature whistles. They probably have signature smells that says, "Hey, I'm Bob," and "Hey, I'm Sue," which is pretty amazing, all in all. And last but not least, I'm going to bring us back to the bison. I said we would talk about the bison, right? So hopefully from what we've talked about, from some of the different methods, you're able to guess how is it that the bison who didn't travel there by themselves, but were trucked down to this new national park, were able to know what direction home was, and also why it was that after multiple generations, they stopped living in the northwest corner, and after about 15 years, they finally expanded to the south side of the park, right? So they are also migrating and using mostly magnetite, and so they could tell the direction of where they came from, just like the pigeon, just like the gray whale, based off of that. But again, if you think about the generational knowledge, it's not necessarily that that's communicated, right? Or I should say that magnetism isn't communicated from generation to generation. The habits are, right? So the fact they always stayed in the Northwest, but then once you get a couple generations later, they don't have that sense of being home there anymore. The new calves that are born, home is where they are, and that is now the place that they will spend generations migrating through. So all in all, I hope you've learned some fun new ways to travel. Maybe it sparked some new different thoughts. And I will pass it back to you, Kendall, if folks have any questions.
Great, thank you so much. That was really fascinating, and it's always really interesting to hear things like nature versus nurture. Where is home versus the biology of my navigation system. So thank you so much for sharing that with us. We've got kind of a shy audience today, so I just want to invite everyone to submit your questions in your control panel in that questions field for Kristina before we wrap it up today. And also, really quick before we get to the questions, if you're interested in any of the trips that she just mentioned, definitely give us a call. That phone number's on the screen, or you can visit our website. All of those trips are obviously on our website and available for you to peruse. Okay, one question that just came in. Is there a main animal that helps lead the flocks?
Ooh, okay. That very much depends on which species we're talking about, but the general answer is yes. And it's not that they're necessarily better navigators. Um, Maybe same as in the human world. It depends on personality. But I'll just pull on a few different examples. So first of all, with bison, there is definitely like a social hierarchy. Um, and there are kind of like boss cows, and they're the ones that are deciding what the herd is up to and sort of where the directions will be going. A fun one is also migrating geese, which is that, so if you think about the V, right, it seems like whoever's in the front of the V is kind of in charge of where everybody's going. Um, so it is that there is certain geese that will go there, but it's not actually a hierarchy thing, it's an energy thing. Being the point of the V is the most energy consumptive. You kind of have, everyone else has a little bit of a windbreak happening behind them. And so they will continually cycle over who's sort of leading that charge and then giving the one who is literally breaking trail the advantage to sort of cycle back. It's also really cool when you watch, right, different migrating birds shifting that formation, or they'll break into a new V or vice versa. But that's the logic behind that. It's about sharing the energy rules. And then obviously you can switch into things like wolf packs, and then it's, yeah, less about, yeah, I would say it's more about behavior in their social group than it is necessarily strength of navigation. But again, that's a human side looking in. It's hard to say. Maybe they would say otherwise if we could ask them.
That's really interesting. So the next question is something that had occurred to me too. How is climate change affecting migratory pathways? And you had mentioned earlier about environmental differences altering things, and I had in mind also about like human behavior. And one species that came to mind was the monarch butterfly.
Yeah. Oh man, this one I almost thought about doing this as a two-parter. Maybe I can or should. Um, I kind of just focus on the what is and less on the what is changing. But yeah, so if we just take a quick nod at each of those, um, let's think about animals that are using sort of seasonal migrators, right? So those cues, we talk about them being linked to sun, but they're often linked to temperature. And the trick is that in their current environment, so let's use snow geese as an example right now. Snow geese are coming south to north. Their cue is on time in the south. They leave, they take off. But when they get to the north, things have actually warmed up faster than what they anticipated, and then they actually can miss certain cycles of food sources. So if you think about these massive tracts of areas that animals are covering, um, and you also think about how there's sort of microclimates and how climate change is changing some much more quickly than others. It means that there's this disconnect in timing and arrival. So they've according to the sun, they've arrived on time. According to that ecosystem that they're jumping back into, they might be too early, they might be too late. And so that can really affect sort of energy or productivity in a system. And then if we shift over to animals that are more like mental mappers or that are using cues, and this is a big one in different ways, but habitat fragmentation is a really big thing, right? So one thing, in forestry is there's a certain area size around, I'm going to use marbled murrelets here on Vancouver Island as an example. They're an endangered, on the endangered list, but they require old growth species, but you have to give them a buffer zone. And part of that is because so that initial navigation is based off of so many trees. If you actually change, if you cut down the forest and change the trees, even if the nest is still there, in theory, they actually won't necessarily find their way back because you've removed too many mental map cues. right? So land use changes make a big difference. Climate change does. Um, yeah, it's one of those ones where there's only, I guess it's kind of trying to shore up different ecosystems in ways that we know that can hopefully benefit. And uh, I don't like the word preserve. I think that you can't really preserve nature. It's not like a jar of jam. It's not meant to stay the same. But hopefully we can do a little bit better on the conservation side of being conscious with some of the changes that we have made and sort of bringing, yeah. I don't know about undoing or going backwards, but I think that we can try and do better out of that and work on a few of those things.
A couple people here are wondering about elephants, and in particular, finding water holes, and I think that can apply to a lot of African species. And I know Africa is not necessarily your continent of speciality, but I wonder if you can speak to that at all.
Yeah. So I will say, thank you, Kendall, for also saying that. Um, I am not an elephant expert, so by all means, hang out with one of our guides in the next couple days who is, and maybe pop a question for them. But it does come down to sort of a few basic systems. So one of it is mental maps from youth. So if you think about existing water holes, right? Again, there's that generational knowledge transfer, which is huge because they do have like functioning family groups. And then when you think about finding new water holes or coming across them, so I think that comes into, again, sort of those senses that we've become disconnected from. So smell is a huge one. And it's not necessarily like smell of water, but think about how much an ecosystem changes, and not just there's the immediate vicinity, but and how much that would then kind of like waft away and cause downwind directions. So that is a big one. I'm guessing sort of vegetation cues that way. I'm going to leave it at that, though. I'm not going to overstep. That's as far as I think I can answer it fairly.
Okay, that's fair. Final question we'll take today because we're short on time. Someone's wondering about the migration of the Arctic tern and what they're using to help navigate.
I would say that they would definitely be a mix between sort of magnetite, right? They've got a big voyage as well. And then their cues are going to be really sun related. So I think our long voyage migrating birds, those are kind of the big important ones. Yeah, I would go with that. There are a lot of species to investigate. It would take a long time to get them all down pat perfect.
Well, you provided a lot of information. It was really fascinating to learn about all of this. I'm so happy to be back hosting for a bit here because I always learn so much. Thank you so much, Kristina. I'm going to hand it back over to you for closing comments.
Thank you, Kendall. Thank you, everyone, for who tuned in today. And I just want to say good luck on all of your travels. Enjoy all your navigation. And navigation is both the literal, sort of finding ways through the world, but kind of navigating through new spaces and places and bringing them with you where we go. So that is my hope and wish for everyone today. Thank you all so much.
All right. Thanks again, Kristina. And thank you to everyone who tuned in. Join us tomorrow for our next Daily Dose of Nature. You can check out the rest of this week's lineup, including registration links, on our website at nathab.com/webinars. And remember, you can always check out all those trips that she mentioned earlier on our website, or you can give us a call. We did record today's presentation, and we'll have the replay available on our website soon. And with that, I will conclude the webinar. Goodbye, everybody.